don't know why I'm attempting this, but here we go, recording again. Hope it works for you. This is the deal. We just found out, red's not, we gotta go, let's go red. 1 over 1 minus x, no, 1 minus x. We just found out is 1 plus x squared plus dot 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 x to the n plus dot dot dot. That's a neat discovery. In fact, that little piece of knowledge is one of our series that you have to memorize. 1 over 1 minus x is equal to e, that summation symbol. Can you not take me seriously, Ross, with this apple in my hand? I can tell. That's the same as x to the n in that summation. That's one of our known series that we have to have tucked away perfectly. I have a list of those, by the way, that you can look at. We have e to the x. If you can remember, e to the x is 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial. That one happened yesterday. There's cosine of x and sine of x. Sine of x. Shall we make a quick short list real fast just so you guys can have that in your...
We still have to do like 2 more parts of example 2.
We will. We'll come back to it. We're going to mess with it first. So before we finish up example 2, we're going to take what we think we know in that last example, which, by the way, is stuff that you do know. I love to come up with 1 over 1 plus x, and my reason is I'm about to run out of battery. I want to get this far. This little dealio. If you have a Maclaurin series centered at 0, you can manipulate the series into something you want. If it's centered at something other than 0, it doesn't work with standard practices. You have to try something else. You can't just do this substitution thing. So we learned yesterday that there's a couple things we can do. We can substitute different things into a Maclaurin series to get a new series. We can derive it. We can integrate it. We can add them and subtract them. We can multiply variables through them. And we can generate new series. So by knowing just a few series, we can actually generate a whole bunch more, which is really cool. So this is the next step. If I just substitute in negative x, I'm effectively getting 1 over 1 plus x. And by doing that, all I'm doing is instead of x, I'm replacing each of these with negative x. And if you think through that, that means I'm going to change the sign of all my odd-powered functions, but leave the even ones the same. So putting a negative x in there changes all the odds, plus dot dot dot. And notice that it's alternating, left positive, negative, positive, negative. And we've got a trick for that. Negative 1 to the n will cause the alternation. And then to make that x to the nth was, but it looks like it's just x to the n, nothing fancy, right? Awesome. So it's just like the last series by putting it, but it's alternating. Same thing, but alternation. So that's how we generate another series. So now I'll go back, since my screen seems to kind of be working. Beware, it might do something crazy. Okay, so we're going to add this blank screen. It's going to have a cool backdrop. There's one other way to generate a series. So this would be part C in that first example that I did complete, example 2. If I were to take 1 over 1 minus x and simply do what it's telling me to do, if I could just follow directions, isn't that division? Last I checked. It's just division. So what I'm going to do is I'm going to divide them. 1 divided by 1 minus x. You ready for this? How many times does 1 go into 1? That's right. Good job. 1 times 1 minus x, 1 minus x. Change the signs. Add them down, you get x. How many times does 1 go to x? 1 times x is x. So multiply through the x times that whole thing. So that's x minus x squared. Change the sign, add them down. X squared. How many times does 1 go into x squared? X squared times. Multiply through. X squared. Oopsie. That's crazy. Minus x cubed. Change the sign, add down. I don't know about you guys, but I think it's just going to keep going. And I'm going to have x to the n. It turns out 1 divided by 1 minus x through long division produces this crazy thing over here, which is the series we just got from using Taylor's kind of practice, Taylor's theorem. Isn't that cool? So I'm thinking maybe people are doing long division, so rational functions can be written as polynomials. That's what really is being said. I can turn this rational function into a polynomial simply by doing long division. And then Taylor's theorem can do it for all different kinds of functions, but we just found out that this backs up what we already knew. Long division is a standard thing to do. They're equivalent. I'm just dividing the two. So, oh man. And in fact, it becomes a tool. There are rational expressions like this. Long division is a means to getting your series for rational expressions. So we like this. Rational expressions. That is one way you can use long division. I'll put in a can in there. Can use long division. Got it. Excellent. Now, the other option that says in there is to manipulate a geometric series. We'll get to that when it's needed. Right now, we can live without it. We're going to go back. Let's see, where am I again? Hitting forward. Okay, back to this one. Well, man, we're on example 6 now? Did I kind of skip a few?
Yeah.
We did? Did we not do 4? Okay, we're going back. Ooh, there's 3. We did 3. It was 4 we needed to get after, right? There's 4. 4. Just talk back to me. Okay. 1 over 1 plus x. That wasn't just, you heard that, right?
Yeah, I heard that.
Okay.
I think everyone did that.
My screen talked back to me. It just said what I said.
Yeah.
It was like me. All right, check it out. Isn't that what we generated for 1 over 1 plus x? Okay. How do you want to come up with x over 1 plus x? Any cool ideas? Tyler's got this one. Tyler, bring it home, man. I want x over 1 plus x. Come on. How would you go from here to here? Woo! Bingo. Multiply by x. Guess I have to write times x without a x. Times x. So if you multiply by x, that's the only difference between them. You can multiply through by a common factor of some kind to get a new series. So it creates x minus x squared plus x cubed minus x to the 4th minus x to the plus x to the 5th. Isn't that cool? Plus dot dot dot. Now, we should check this out. Everything's a little different, and we have to be careful how we start this, because what I want is I need to put in the n's, the powers of n's, in a way that it generates the right terms. So I need to start out with, let's say, n equals 0, and if I call this the n equals 0 term right here, is x, I need to put the powers of n so that I get the right thing. So if we put in 0, how am I going to get x in this particular thing? And it has to be positive. Ooh. Isn't that goofy? Well, think what it did to the general rule.